Welcome back after the break. I'm sure we're all refreshed and you took a sip on something that you enjoyed. Please hang in there with me. We will be going on. Before the break, we spoke about the Kc expression, and now I would like us to go and work with Kc calculations. Remember what I said? Kc stands for equilibrium constant, and the most important thing that you should remember is Kc is only affected by temperature. It must be like a rhyme for you. Kc is only affected by temperature. I would like us to look at the question. Ammonia is prepared, ammonia is NH3, is prepared according to the following balanced equation. Remember, I said it's important to know the balanced equation because we use the coefficients that becomes exponents in our Kc expression. At a low temperature, and this temperature is 350 Kelvin, an equilibrium mixture for the above exothermic reaction has the following concentrations. They tell us that at equilibrium we have the concentration of ammonium is 2 mole per decimeters cubed. The concentration of our nitrogen is 0.5 moles per decimeters cubed, and for the hydrogen gas it is 1.5 moles per decimeters cubed. I just want to refresh your memory again that concentration is equal to the number of moles per unit volume. We look at it. First thing that we need to do, like with any other calculation, we write down what was given. So we were given the concentrations of the nitrogen, ammonia, and the hydrogen gas. The very first thing, please make sure that you always, as soon as you have to calculate Kc, the first thing that you must do is to write down a Kc expression. For this one, remember, this is our products, and this hydrogen and nitrogen is our reactants. Okay. We were given the concentrations, and because we need to substitute the concentrations, we can substitute what was given to us. There's no need for us to convert it into a concentration or to find out what the volume is. Even if we don't know what the volume of this container is, we can still work out the Kc value. So when we substitute into the Kc expression, we will substitute the 2 there with the exponent 2. Then for nitrogen, we have 0.5 mole per decimeters cubed, and for hydrogen, we have 1.5. And remember, for hydrogen, this should actually be a 3, exponent 3 there. So, but if you work out this Kc, we have 2, exponent 2 divided by 0.5 times 1.5. Remember, 1.5 is exponent 3. That comes from the coefficient of our hydrogen. When we work this out, we get to an answer of 2.37. And what does that mean? You must always ask yourself, what does that mean for the Hildhoff Kc? They also ask the question, what is the significance of Kc? When they ask you that question, they actually want you to talk in terms of Kc, is Kc bigger than 1 or is Kc smaller than 1? Now in this case where Kc is bigger than 1, I said to you it means that your products, which is your numerator, is bigger than your reactants, which is your denominator, and that leads to a bigger than 1 value. So what's the significance of Kc being 2.37? You will then say this means that the product is more than the reactants. Another question. Consider the following reaction. We have 2A, which is gas, 1B, which is also in gas phase, that converts into C, that is also in gas phase. What's important is, why do I talk about gas? Because as soon as I have to work out Kc, remember, Kc is working only with gases, and aqueous solutions. Kc, we do not use the L, which is liquid, and we do not use the S, which is solid. We take those concentrations to be 1 because those concentrations remain constant. They say to us further that we have 12 mole of A and 10 mole of B in a sealed container, and they give us the volume of this container. At equilibrium, there are 4 moles of our C and in our container, and the temperature that this happens at is 300 Kelvin. Why do they talk about the temperature there? Remember, Kc is only affected by temperature, so they need to tell us at what temperature this specific experiment is done. So the question there is, work out or calculate Kc. Firstly, you write down what was given, and I want you to see that we have moles now. We don't have mole per decimeters cubed. So I want to remind you that C is equal to N over V. What they have now is they give us the number of moles of A, they give us the number of moles of B, that's in the beginning. Remember, your number of moles of A and B at the beginning is more, and it starts to become less as the reaction proceeds. But at the beginning, you need to remember that there is no C at the beginning. So the first thing, the most important thing that you must do is you need to write down the Kc expression. Write it down there. You can write it down again a bit later if you have to. Just remember, you lose your marks if you do not show the Kc expression. Then, because we're working with mole, we will now first have to go work out the concentration of A, B, and C, but this concentrations, we need to go work out what is the concentration of this at equilibrium. Now, we were told that the concentration, the number of moles here, is 4 moles at equilibrium. Right. When we work with this, we have what we call, teachers call it different things. I call it the rice table. Rice is as in rice that we eat. And I will explain to you now why I call it the rice table. The rice table is an ordered way to do the calculations. You can do it in any other way as long as you keep track of what you're doing. As long as you get to the end point, it's not really about the journey. But the journey that I would like to explain to you now is how to convert those moles into concentrations at equilibrium, and how to then use that concentrations at equilibrium to work out the equilibrium constant, or as we call it, the Kc. We call it a rice table. The rice comes from R, which stands for the ratio, and this ratio, as you can see, this ratio is actually the coefficient of your balanced equations. Okay, so we have a 2 for A, we have a 1 for B, and we have a 1 for C. I also want you to see that the next one, which is my I to make up rice table, is for the initial mole of my A, my B, and my C. The third row, we know that this little triangle that we call delta, we know that we also say that it means change in. So on this row, that little triangle means change in the number of moles. So change is a C, and that brings us to the next row, which is actually the equilibrium row. What is the number of mole at equilibrium? So we then take that number of mole that we will calculate there and convert it into a concentration by using C is equal to N over V. Where does V come from? V was given to us, and V is in the correct unit, decimeters cubed. Why do I say it's in the correct unit? Remember, when you work out the concentration, you need to have your volume in decimeters cubed, because your concentration unit is moles per decimeters cubed. Right, are we ready? What's very important is I want you to note this line here that's actually very bold. That very bold is actually an indication of whatever is on the left-hand side is my reactants, and whatever is on the right-hand side is my product. I want to focus your attention again that we only use gaseous solutions or aqueous solutions when we work out the Kc. We do not use liquids and solids. Back to what we're doing, I would like us to use another pen color. So what we should remember now is initially we had 12 moles of A, 10 moles of B, and we know in the initial states, and I just want to show you there, initially we have that number of moles for A and B, and we have no moles for our nitrogen, for C. So if I started off with 0 and I now have 4, it actually means I must have added 4 when I did the change. Where does that adding come from? Remember, in our forward reaction, our reactants start to convert into product. And as it converts into product, some of the reactants are now converting into the product. Therefore, we say plus. Then, this is a very important row because this row needs to be aligned with the ratio. So we can now say, to have the same ratio, we will say 4 times 1 divided by 1, which means there is 4 of my B. We can go work out in ratio how many moles of A must I have, which is 4 times 2 divided by 1, which is 8. But now we know that we actually used up our reactants, so we will put a negative there and we will subtract from there. Right, so if we look at the equilibrium constant and we look at our Rice table, we are now where we can say, I now have 12 minus 8, which is 4, and 10 minus 4, which is 6, and at equilibrium this was given. Now I know the number of moles at equilibrium, so I can go work out with C is equal to N over V, and we know V is 2, so it's 4 divided by 2, which is my volume, 6 divided by 2, and this is then my concentration at equilibrium. That brings us to the substitution of my concentrations into my expression, where I have C to the exponent of 1, A to the exponent of 2, B to the exponent of 1. And if we put them all in and substitute them correctly, we have a value of 0,17. What does that mean? When we have 0,17, it means Kc is smaller than 1. What does that mean? It basically means I have few products, but I have a lot of reactants. Right. To summarize, I just want to remind you that we spoke about a closed system. Chemical equilibrium only happens in a closed system, only reversible reactions. Your rate of your forward reaction must be equal to your rate of your reverse reaction, and the concentrations of everything remains constant. Then to summarize equilibrium constant, or Kc, the ratio of your concentrations of your product and your reactants, it is expressed from the chemical equation. It only applies to a specific temperature. There's no units because it is a ratio. When Kc is bigger than 1, your products are more than your reactants. And when Kc is smaller than 1, your reactants are more than your product. Thank you very much for your time. We'll see each other soon.